Good morning, everyone. Respected keynote speaker Dr. Amitabh Bagchi, Dean and Co-General Chair Dr. Rudramohan Tripathi, distinguished authors, paper presenters, faculty members, and all the participants present here. A warm welcome to the second day of the International Conference on Artificial Intelligence and Emerging Technology. We are about to begin another engaging session, one that promises us to take into the world of technology, helping us to explore, understand, and gain valuable insights that will enrich our knowledge and spark meaningful discussions. And now, it is my privilege to introduce the keynote speaker of the day, Dr. Amitabh Bagchi. He is a professor of computer science and engineering at IIT Delhi. His primary research interest lies in developing theoretically grounded approaches to real world computing problems. His expertise spans across algorithms, data structures, probability, graphs, and linear algebra, which he has skillfully applied to diverse domains including wireless networks, social networks, databases, Laplacian solvers, food delivery, and machine learning. A distinguished researcher and a renowned academician, his work reflects both depth and impact, making significant contributions to the advancement of computer science. Sir, may I now request you to please take the stage?
Is that? Okay. Okay. All right. Am I audible? Is it on?
I think we need to.
You need to switch it on. Yeah. Yeah. That's it's on now. All right. Thank you. Thanks for very kind introduction. I'm very happy to be here. Um, I don't get out of Delhi much, so it's good to be out to see all of you, students, faculty from other institutions, participants, and of course, Rudra, who some of you may know was my first PhD student. So, first PhD student is always special. Not that second and third are not special, in case not in case they feel bad about it. So, let me give you a little context of the work that I'm going to talk about today. This is work that was done a few years ago, like 5, 6 years ago. But the reason I decided to present it here as a keynote is because what I like about this work is that it is it started with a theoretical idea, some mathematical concepts, and we were able to translate that into a very applied, a very real kind of setting, which is actually useful and being used in day to day. I mean, uh, can be used day to day in the technologies that we are actually using. So, in order to go from theory to practice, uh, different ways of thinking have to be applied, and different ways of the key point is not just ideation but also validation has to be done in different ways, and that's the key takeaway that I want all of you to work towards with this talk. The important insights here are not whatever I'm the specific topic that I'm talking about. The important insight is that if you have a theoretical idea, how do you validate it? When you take that theoretical idea into a real life system or into an algorithmic setting with real world data, then how do you validate over there? What are the questions that have to be answered before a system or an algorithmic framework goes into the real world, right? What are the range of questions, right? In a way, I think I feel that as computer scientists, we are very lucky because we work in a discipline where which is where There's everything from mathematics to very hardcore engineering. And we get to understand and work with all many different kinds of concepts, and that is our good fortune. So the title of this talk is Graph Reachability with Random Walks. I explain, and of course, these are my colleagues and some former students with whom I did this work. So, what is a reachability query? So, you all know what a directed graph is. So, the question is simple: given a directed graph and two nodes u and v, is there a path from u to v? Right now, why is this important? So, the my key collaborators in this, like Shrikanta, Vedathur, and Maya Ramnath, they are database people. And so they work in things like knowledge graphs. What is a knowledge graph? A knowledge graph is a way of storing facts about the world. You know, like so and so is father of so and so, or so and so is dean of School of Computer Science of XIM University, at such in started in this year, so on and so forth. And such collections of facts are described in what are known as RDF databases. There's a resource description framework knowledge bases, right, which have this graph structure because a lot of basic knowledge is coded as relationships. Right, there are names and then there are relationships, and the coding is in graphs. Right, then apart from knowledge bases, there are things like citation networks. You know, how who is citing whom. Protein interaction networks, the biology people do that. I don't know too much about that. Then there is this third point, sparkle property path. So in these knowledge graphs, there are query languages which which query knowledge graphs uh, in a non-simple way. Like, for example, if we take a case of a graph in which you have parent of relationship, right? So then you may say that is there a path between, I don't know, let's say Rahul Gandhi and Nehru in this graph, right? And the answer should be yes, because there's a parent of relationship which connects it. So the query is not giving responding based on an edge, but based on a path, and that path has a certain property associated with it, right? We'll look at this in more detail. And also, there are many other graph processing techniques that need a reachability query to be able to work. So, how does one solve reachability on a graph? Here are the different things one can do. Firstly, is a simple online setup, right? Start a BFS from you. If you reach V, you're done. If you don't reach V, you're also done. You can give a no answer, right? The problem with this is it takes a lot of time, right? The other way to do it is you materialize the full transitive closure. What is transitive closure? Right, you put uv in your transitive closure if there is a path from u to v. You do this for the entire graph and just store it somewhere. Now if someone gives you a particular query, you just look up whether that pair is in the transitive closure, give yes answer. Right, very fast, it takes no time to give the answer. Problem is computing the transitive closure is takes time, right? And then you have to store the whole thing. So most of the effort in the area of graph databases has been in between. You want to store some kind of index from which is not that large, right? But it can give you a quick answer, right? So a lot of different ones. Maybe you've heard of two-hop labeling. Two-hop labeling, for example, is very popular. A lot of people use two-hop labeling, even in the real world, in industry and all. Right, but of course there are many other things. So in this, you just create some kind of index and you try to answer the question. So what's the problem with index-based methods? Right? Okay, queries are very efficient, but there's a high cost of update. Right? If you can see that here, whenever there's going to be an update in the graph, like an edge gets added, a node gets added, now I have to update my whole index. Right? So that's a problem. So a lot of the work in these index-based research is in showing, okay, you know what, my index looks in the like this, and in an update, I can bound the time in which I will update the index so that is correct. Right, it's a data structuring kind of problem, right? And I'll give you this good time. And often, in order to make the index updatable quickly, you have to make it larger, store more things, right? And for query efficiency. So suppose we say, okay, we are not going to have any index, so there's no memory overhead or very little memory overhead, no update cost, but okay, queries will be slightly slower, not as slow as BFS, slightly slower. Then you might say, I'm not saying you will say, but in certain situations you may say, okay, I want this solution. Okay, so this is the solution I want to present to you. But first, we are going to have a little theoretical digression. So probability game, balls and bins. There are n bins, uh, n balls, two n balls, n of red, n of green, right? We are or k of red and k of green, and we are allowed to throw k balls of each color into the bin. So this is the, you must have seen this balls and bin game. You take a ball, throw it into a random bin chosen by some probability distribution, right? But now we have two colored balls and two different probability distributions associated with them. All right. So you have red balls, the probability distribution is mu over the bins, and green balls, probability distribution is nu. Question is, how large should K be to ensure that there is a bin with both a red and a green ball in it? Okay, you understand the thing? Right, I have this set of bins, I'm throwing red and green balls, and I want to achieve a situation where there is a bin with both a red and a green ball, right? And there are these two, and you can see, like, suppose mu was the probability that the probability distribution mu was that in bins 1 to n by 2, I will put my red ball uniformly, and nu was that in bin n by 2 plus 1 to n, I will put my balls uniformly. Then there will never, this will never happen. You can do it whatever you want, right? You can see that, right? Now, what if the mu was the probability that I will put my or any ball will go to bin number one, and nu was the same thing? Then it will always happen. You just need one ball, and it's done, right? In general, we are not interested in these two degenerate cases. We are interested in intermediate case. There's some mu, there's some nu, right? And specifically, we are interested. And also note one thing: whatever the well, not whatever the probability distribution. Suppose you had a situation where you were well, you can say that if I have n by 2, it's not obvious. If you have you can see that if you have large enough number k, right, you have more and more chance of getting an overlap, right? But we are looking for a small number, small meaning little o of n, right? That's what small means for us. Okay, so this is the game that we're going to play, right? And okay, there's a little bit of maths here, but just follow with me, and we'll be fine. So I have this random variable xi, which is one if bin I has at least one ball and at least one green ball, zero otherwise. So, and probability pi is the probability that xi is equal to 1. So what is pi equal to? Well, it's the probability that, so what is this 1 minus mu I to the k is the probability that none of the k balls lands in, none of the k red balls lands in bin I, right? So 1 minus that is the probability that one of them lands in bin I, and same for the green balls over there. So product, right? Now, with a few conditions, I approximate this to be greater than equal to k squared mu I nu I divided by e squared. Mu I is the probability that the ball will land in uh, bin I, the red ball will land, and nu I is the probability that the green will land in nu I, right? So this, and you have a k squared over here, and you have a e squared down here, because this is, there's some approximation that has taken place. Let's not worry too much about what that approximation is. All right. So now that was for a particular bin I. Now I want x to be sum of xi. Sum of xi is what? sum of xi is greater than 0 if there exists one bin which has both red and green, right? Because xi is equal to 1 means that in the ith bin you have both a red and a green ball. So sum of xi is actually the number of bins which have overlap. So all I'm interested in is sum of xi greater than 0. Sum of xi is greater than 0, there exists a bin which has both a red and a green ball, right? So what is the expectation of xi? Based on the previous calculation, we can say that expectation of xi is greater than k squared over e squared times alpha mu nu, where alpha mu nu is this. I is equal to 1 to n mu I nu I. Right? It's a measure of overlap of the distributions. In fact, you can say something quite precise about this. Suppose I had a random variable x with distribution mu and I had random variable y with distribution nu, right? And they were independent of each other. What is the probability that these two give the same value? Is precisely this. Have a look, right? It's precisely this. If I have a random variable x with distribution mu and y with distribution nu, right? Then what's the probability that this one gives I and that one gives I? Mu I, nu I. What's the probability that they give one of them some I such that they are both the same? It's this, right? So in the case where both of these distributions are uniform over all bins, you can calculate easily. This is 1 over n, right? Because it's 1 over n squared summed over n terms, right? And it's also possible to show that this overlap is less than 1 minus nu minus nu total variation. This is a standard way of writing distances between probability distribution. Okay, so there's this overlap concept is there, right? Oh, sorry, went the wrong direction, right? All right, maybe we don't need to go through all of this in great detail, but once you write it down like this, you can use this theorem, McDiarmid's theorem, right? To show that the probability that x is equal to 0, this is the bad case, x is equal to 0 means there is no overlap, right? This has an upper bound which is related to the number of balls, the overlap, and well, this is actually just number of balls because k4 and k will cut to give k cube and the overlap, right? So the higher the number of balls, right, the higher the overlap, the smaller this probability, because you see it's a x minus. Higher number of balls, higher overlap, smaller the probability that x equal to 0, which is to say that you have failed, right? The fail to get an overlap. That probability is will be low if k is high and overlap is high, and that's what we expect. But this gives us the exact kind of characterization in terms of these numbers. And I'll just tell you what the final result is. And the final result is this, that if you throw k star red balls and k star green balls with probability distribution mu and nu, such that k star is n squared log n divided by alpha mu nu squared to the 1/3, right? Then with probability at least 1 minus 1 over n, you will get one bin with overlap with there's some mild condition associated with it. So now, as long as your alpha mu nu, if your alpha mu nu is something like a constant, right, then this is a good result, because this will give you square root n to the 2 3 sorry n to the 2 by 3 and log in terms, if assuming this is a constant, right? So that is a little o of n result, right? So this is very nice, that as long as these two overlap well with constant amount of overlap, so that uniform distribution won't do the trick, right? Because in the uniform distribution, this alpha mu nu is actually 1 over n. So this becomes n4 to the 1/3. So that's too many balls, right? But if I have a good overlap, then I will be able to do this, right? So actually, for the uniform distribution, you can analyze it in a different way, but let's not get into that. Let me just keep on track of the time. Question is, what is all this got to do with reachability in directed graphs, right? This doesn't, I mean, we started talking about that. So here's how we're going to do it. Given a graph G, let G prime be the version of G with the edge directions reversed. Now what we're going to do is we're going to run K star random walks from U on G for L steps. What is a random walk? A random walk is a sequence of vertices on a graph. And how is that sequence generated? You start with a given vertex, say a given vertex, or you can start with some vertex chosen at random. And then from there, you look at all its neighbors, out neighbors, right? Because it's a directed graph. You pick one of them uniformly at random, and that is the next vertex. Then what do you do after that? That neighbor, that new person, that person's neighbors you look at, pick one of them uniformly at random, and that's the next vertex in the sequence, and this is called a random walk. So you can imagine a pebble, it starts at some point in the graph and it just starts moving using edges which are available, chosen randomly from the set, right? So that's what a random walk is, and you can see that like the path that you get to the random walk is contained in the BFS, but actually you can think of it as a sample out of the BFS path. So in the BFS you have all paths there. Here you are just taking one path in the random walk, right? So what we're going to do is we are going to run K star random walks from U on G for L steps, where we'll talk about what L is going to be, and let FU be the set of endpoints of those walks, right? Run K star random walks from V on G prime for L steps. Let BU be the set of endpoints of those walks. If FU intersection B, actually, sorry, this should be B V. If FU intersection BV is non-empty, then say yes. What does it mean FU intersection BV is non-empty? Right? It essentially means that, wait, I have a diagram here. Let me, right? So from here, you start from V, you put these random walks, you put these random walks. Suppose this set of red and green has a common vertex. What does that mean? That common vertex is a witness to the fact that V is reachable from U. Why? Because you can walk forward from U to reach that common vertex, and you can walk backward from V to reach that common vertex. Right? So that so this if the intersection vertex exists, you can definitely say that yes, these U and V are reachable. V is reachable from U. The only problem is that if I say no, it is not reachable, right? That means all I'm saying is that I took some random paths from here, I took some random paths from here, they did not intersect. That doesn't necessarily mean there is no path from U to V. It just means that the random, it may mean that there's no path from U to V, or it may mean that the random paths I took from U and from V just didn't happen to intersect because I didn't choose the right paths, because I'm doing it probabilistically. So there's some probability that I might have made an error, right? So the analysis that we did earlier about this red and green balls, this is going to help us show that the probability of getting such wrong answer, the only wrong answer that is possible, is a false negative. False negative means I say no when the answer should have been yes, right? So the kind of analysis we did earlier will show that the probability of false negative is low. That was why we went into that whole discussion, right? And the mu and nu are going to be the distribution of the random walks after L steps. The forward distribution after L steps, the reverse distribution after L steps. All right. There are some questions that remain, like, so that's a theoretical idea, but to take the theoretical idea and to actually run it on a real world graph, etc., we have to answer some questions. What is the value of alpha mu nu? How do we decide what is the right value of L? There was that condition. Do we know whether it's satisfied? Do we really need to conduct so many walks, because that number n to the two-thirds is still quite large, right? I mean, if n is, say 1 billion, right? N to the two-thirds is a million, right? That's still quite a lot of walks. Do we need? So these kind of questions now, the theory is kind of over. Now those questions have to be answered in the real world, right? So as we said earlier, benefits, there's no index required, so small update time, very little memory overhead because you just have to maintain these f and these sets f mu fu and v, right? And it's very parallelizable because random walks, you're just running random walks, very heavily parallelizable, right? Anything with random walks or this kind of sampling is very parallelizable. And we all have these multi-core and we have GPUs and all that. In fact, one of my current students has had some success speeding up random walks using GPUs, speeding up situation, not in this particular setup, but in situations where we need to run a lot of random walks, running them in parallel works very well on GPUs. Uh, and drawbacks, well, false negatives are possible as we discussed, and they're slightly slower than index-based method because you have to do something, you have to walk out. Index-based method is just a hit the hash table, and the answer is sitting there, right? That's what they get, right? So we will. Uh, what is my cutoff time? 45, 40. 45 is the cutoff time. Okay, that's fine. We will apply this idea to reachability over complex and annotated graphs. So firstly, dynamic graphs, right? Edges and nodes are being inserted and deleted. Most graphs in the real world are dynamic, right? There's always some change going on. Even our like even map data is dynamic, right? Like for example, if not inserted and deleted, then like for example, if you take the road from the airport to here, right, that is halfway between inserted and deleted, right? So in dynamic graphs, as we said, reindexing is expensive. Then there are temporal graphs where edges exist for a particular amount of time. A classic example would be, let's take airline data set in which whenever a flight is going on, the edge is said to exist. So each edge will exist while for depending on the length of the flight. So and we'll see an example of that. And then there are labeled graphs where which we talked about already. Like the father of, friend of, etc. kind of things, right? So with constraint, if we get time, I'll discuss that. So these are the two papers. Those are the names of the algorithms, and we published that first one on dynamic graphs and temporal graphs in ICT, and the second one on this labeled graphs work was in Sigma 2019. So let's quickly talk about the dynamic and temporal graphs. So this part we already discussed, FU intersection BV. The point is that we have to decide what is the length of the walk. So we choose the walk length proportional to the diameter. There's some mathematical reasoning for it, but you can imagine that if you're walking less than the diameter, then you're increasing the chance that you're not going to meet from this side to that side. So about diameter, this leads to a certain overhead because we have to estimate the diameter of a real world graph, which is not a simple thing to do. How do you find the diameter of a graph? Anyone? How do you do that? BFS, right? You have to at least BFS. Or I mean, if you want to do Warshall Floyd or something like that, that's even worse, right? So how we have to quickly be able to estimate the diameter, otherwise we'll be in trouble because in a dynamic graph the diameter changes. So the way we do it is we pick a few random pairs in the graph, like 10, 15 of them, and find the length, the distance between them, and the maximum which use as the diameter. And that it's a reasonable proxy for this. And then the number of walks which we set to this, and there are some hyperparameters you have to find what constants you have to apply to this. So let's talk about performance. We for dynamic graphs, we compared our method, which we called arrow, to BBFS, which is bidirectional BFS. That is, given U and V, you start a BFS from both sides. The moment they meet, you give a yes answer. If they complete without meeting, you give a no answer. And then we compared against this other paper, this method called Dagger by Yildirim et al. So what these people do is they compress the graph into an equivalent directed acyclic graph. So you can see that any directed graph has a strongly connected component. What is a strongly connected component? It's a set of all vertices such that there's a path from U to V and V to U, right? So if you take a directed graph and you you compress all the strongly connected components into single nodes, this is going to be a DAG. Why? Because if it was not a DAG, then that means you didn't have a maximal strongly connected component. You would have had another. So what they did is that they made this strongly connected component DAG, and then they answered their reachability queries on that. If two vertices belong to the same node, same strongly connected component, yes. If not, then it depends on where they are. So their problem is that every time there's an update, they have to update this DAG. So what we did was these are two results I'll show you. In the Flickr data set, we started from a large number, about 2.3 million, right? We inserted I mean, sorry, these are the nodes. We started from about 17 million edges, inserted these many, then deleted all of them in bits. In this case, we started from a very small number, right? Inserted up to a very large number, and then deleted back down, right? So this is the story, right? Basically, what happens is that our method arrow, right? It's slower than dagger, which is to be expected because they have it's like an index, but it's much faster than BBFS, right? But what happens when you start inserting and deleting? In that case, you can see dagger is up here, like 100 seconds for delete, I mean 100 milliseconds, whereas you can see that arrow is here, BBFS is here. BBFS doesn't need to maintain anything, you just run it, right? If when you do an update, right, all it needs to do is just update the graph database, which we also need to do, but we need to re-estimate the diameter, so we have to spend a little bit of time re-estimating the diameter. So that's why we're a little slower than BBFS when an update comes, but much faster than Dagger, right? So we lose to Dagger in query time, but we win majorly in updates. And then if you do the mix of, so it depends, right? If you had a very static database with a lot of queries, then I would say use Dagger. But if there are a good number of updates, then don't use Dagger, right? So you can see the result on that side. Okay, so here are temporal graphs. Let me quickly tell you what those are. Like things like transportation networks, social networks, this, that. So you can see that over here there's an example, and these numbers here tell you what is the time at which the edge exists. Right. So this edge exists between time unit 1 and 15. This one between 1 and 20, and so on and so forth. Right, and there are different kinds of reachability queries in this. We're going to talk about snapshot paths and chain paths. I'll just explain those in the next slide. And this is a very important problem in graph databases. So there is work on this, but again, here the indexes are even more complicated because time also has to come into the picture. So it takes the indexes become specialized, and now the problem is that the different kind of reachabilities also they have some trouble answering, which is a little easier for us. So here's a snapshot reachability query. So like a snapshot reachability says that you look at the graph as it exists at a particular point in time and then answer the query on that. So like for example, Alice followed Bob on Feb 10th and Bob followed Charlie on March 9th, right? So now, like, if we from this we can tell that if Charlie made a posting on March 10th, then Alice will Alice be able to see it? Answer is yes. But if Charlie made a posting on March 8th, then Alice will not be able to see it, right? So these are related to specific times. Or you can ask the question, in March, if was Alice able to see some of Charlie's posts? You can say yes, some of them, right? Whereas for if you ask the same question for February, the answer is no, none of them, because at that time Bob had not yet followed Charlie. So that's a snapshot reachability. Now this is chain reachability. So these are the flight examples that I gave. Now the thing is that if a flight starts before, if your connecting flight starts before your current flight has ended, you cannot take the connecting flight. Connecting flight has to start after your flight has landed. In fact, normally they, if it's less than 1.5 hours or so, they don't even allow that connection in case of delays, right? So that's what we call a chained query. So I want a path from U to V through edges such that I, whatever my starting time in the query is, the first edge should start after that starting time. The next edge should start after the first edge has ended, and so on and so forth. So you can either, I think just the example of getting from one city to another via connecting flights gives the idea, and there are other applications for this also. Now, what happens is that for our arrow method, we need a little more. We can't just be random walking around. Now, one thing we need to understand is that how are these graph databases, temporal graph databases stored? So the way, typically the way graph databases are stored is they're like an edge list. Or if you have a vertex, you can query the set of edges associated with that. Now, the time annotation that this time is available from, this edge is available from time 1 to time 15, this is actually written on the edge. So it's only after you retrieve the edge that you can read what the time associated with it is. So now that causes a problem, because in our random walk, we are retrieving edge at random from the database. But it's only after we retrieve the edge that we look at it and see what the time. Maybe it is not the right thing for us. Like, I have taken a flight from Delhi to Kolkata, right? And I've arrived at 10 a.m. Right now, I'm looking for, say, a flight from Kolkata to Bhubaneswar, right? And I pick or I'm looking a flight out of Kolkata. I pick an edge, right? Fine, it says Kolkata Bhubaneswar, but the time is 9 a.m. Now what do? I pick another one, right? I keep picking till I get one which moves me forward, but also has the right time. So there's a bit of there are certain kinds of issues that uh, come up here. So we have to be a little careful in managing these kind of things. So again, the state that we have to maintain becomes a little more than we had earlier, and the decisions we have to make are a little more complex. So it's not just simply random walk and we'll see what happens. So we compared against a couple of different methods. One was this what is called time reach, the one I mentioned earlier, top chain, etc. Right now, here what happens is that when the path exists, time reach is much faster, right? But when the path doesn't exist, our method is much faster, because they keep looking even if the path doesn't exist. Whereas because we do these random walks, we stop at a certain time, we are able to say no faster. And of course, we don't have the problem of maintaining the index and so on and so forth. And the same thing happens, there's another one also called top chain. The same thing happens with them as well. Okay, so I have 5 minutes. So let me very quickly tell you about this one, and I'll finish. I won't go into a lot of detail. So label graphs, right? So you look at this graph. Here there's some people and there's some edges between them, and here the nodes are labeled male, female, etc. So is there a path from V1 to V7 with the pattern male, female plus? Right, this is a regular expression, and you can see that the path V1, V2, V4, V6, V5 has this thing, because you have male, female, and then you reach the destination, right? So this is like a regular expression like what we saw in theory of computation, right? And this in Sparkle's property paths have these kind of semantics. Like I gave the example of, is this person ancestor of that person, right? So there you can, or you can imagine like, are two people related? So then you can take edges which are of the form son, daughter, father, mother, uncle, those kind of edges you can take. And this is something actually, one of my colleagues, he does this work, that he has done this work where they download these corporate databases and they try to find linkages, because you know how big business, they do these funny things, they make these shell companies and they move money around. So one way of finding out who is related to whom is by creating this graph, a knowledge graph of who's a relative, or who has worked with whom, or who has worked for whom. Then if you have these two companies which are unrelated, but there's actually a path with these kind of relations between them, then you know that, oh, these people are trying to pretend that they're unrelated, but actually there is some connection. So this kind of work actually people do in network science for studying corporate structure and all that. So finding these kind of paths is NP complete, unlike the previous case where there was no NP completeness barrier. So that is a bit of a problem. Um, okay, I'll jump through this stuff, right? And here the problem is that there's a labels set of labels that can be applied, and that set of labels could be very large, right? Like for example, we looked at Google Plus, which was this social network Google used to have. It had, in that data set, there were 17,000 labels, whereas our most previous competitor, their space complexity, it was an index-based method, space complexity was exponential in the number of labels, right? So I mean, forget about this, and you can see that even at 10 labels where they had reached, so you can imagine where they would reach at 17,000 labels. And previous works also, because of this same problem of indexes blowing up, they weren't able to like handle a lot of different regular expressions. So in our case, essentially what we do, it's quite simple, is that you have a regular expression, you do the same bidirectional thing, except that when you take the next edge, you check whether it satisfies the automaton associated with the, you all done automata theory, right? So, you have an automaton, you have a string, and the automaton consumes the labels. If it consumes the labels, you can move forward. So here, we build the automaton, sample an edge, look at the label. If that label can be consumed by the automaton, you can move forward, otherwise sample another edge. Earlier it was about the time checking. Here the checking is with the automaton. So that's the only difference, right? And um, so basically, we were able to perform much better than the existing things. Only difference is that the existing methods had 100% accuracy, and in our case, because we have this false negative problem, we have accuracy, but our accuracies in most cases are very high. In one case, it was down to 86%, but normally it's in the 90%. If it had been less than that, we wouldn't have been able to publish this work actually. So luckily, it was good enough. So yeah, so that's this is the same thing. Let me just go to the conclusions now. Right, it's already 10:45. So basically, what are what is our takeaway message to the graph database community, right? This is the takeaway message for those people who work with graph databases and are thinking of how best to implement reachability in graph databases. So our takeaway points are that, okay, it is very practical to random walk in the graph, right? Indexes are very fast if the graph is static and queries are simple. Graph has few labels, memory is available for the index, fine. Otherwise, use our method. And in most practical settings, you don't have all these assumptions which because of which index-based methods work, right? Random walks can be parallelized easily, integrated into normal graph stores that we have, all this Neo4j and all that, right? And to move forward from here is to actually implement these methods inside graph stores and then use these methods to build other algorithms and see what happens to the performance of those. So I had to skip a few details, but I hope that you got the big picture. The picture. Thank you for listening so patiently to this talk. There, any questions? Please feel free to ask. Yeah, no, that's a very good point. So the thing is that this was a key issue, right? That if this overlap alpha mu nu is very small, then there is no guarantee. But the thing is that a lot of real world graphs, which tend to have power laws and so on, they tend to have some kind of hubs and all where a lot of overlap takes place. And so those hubs play the role which give you a good enough overlap. So what we did was, and in network science there's also this concept of assortativity where you have two people with high degree are linked to each other and so on. So what we did was we studied a bunch of real world graphs and tried to figure out how is this related to assortativity, the overlap and all. And we found that in general, the overlap is good for real world graphs, but that is actually only part of the picture because the theoretical result is a little pessimistic. Theoretical results are always pessimistic. What you see in the real world is always better. So we found that even in cases where the measured overlap was not as good as we would like it to be, using a smaller number of random walks gave the right answer. So because all the results that you saw against the baselines, they are all done on real world graphs. And there our accuracy was in the 90s, except it's only when we came to this labeled reachability, which is a very complex problem and there are no theoretical guarantees for that. There our accuracy came below 90 for the first time. Otherwise it's for arrow it is always in the high 90s, even when the measured overlap is low, right? And so the theory gives a direction to think, but it is not the end of the story. Finally, end of the story is what you measure in the experiments. Because if you want people to put it in their systems, I'll tell you one thing about this work. Even now, graph database community is very leery about it. They're like, oh, you may give a wrong answer if the answer is no. We are not very happy about it. They are happy to use machine learning techniques where they even know, yes, all can be wrong. But this they'll be like, no, 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 no. So they are still suspicious about it. This, especially this regular expression reachability work, a lot of follow up work has happened after that. Yeah. Any other questions? Yeah. Huh. No, when we walk from we flip the direction of the edges. So it's the reverse then side. So because in the graph data we can ask for a random outgoing edge or a random incoming edge. In most graph databases you store both these sets with. All right. Okay. Thanks again for listening. Thank you. Thank you.
Thank you, sir, for such an insightful session. It was truly an honor to have you with us today. Your thoughts and expertise have given us valuable perspective and have inspired every one of us present here. As we conclude this session, I now invite our Dean, Dr. Rudra Mohan Tripathi, to present the certificate and token of appreciation to our keynote speaker, Dr. Amitabh Bagchi. Thank you, Amitav sir, Dean sir, paper presenters, faculty members, and everyone for your presence. Now we'll have a short break for tea and snacks. The sessions will resume from 11 a.m., so please reconvene at your respective sessions by then. Thank you. Yes. Technical session 7 of seminar hall 6 is shifted to seminar hall 3.
पता नहीं अंत किसका नाम पे देखते हैं नहीं किसी का नाम ठीक है निकल दो कोई प्रेजेंटर होगा ले ले
छोटा वाला, हाँ ये रहा।